from Indonesia, Yusuke from Japan, Yasintaha from Kuwait, Joseph Chidera, Wajil Hawkins, Ayonut Bogdan from Romania, Anton from Russia, Marius Spain, Mohammad Sri Lanka, Chunju from Taiwan, Siravich from Thailand, Olina from Ukraine, Kate from the US. And then stand at the side. How many people will speak is up to the team, and you will be handling your own presentation, changing the next slide, etc., etc. Is this all right? Yes. So who is the person who will handle the PowerPoint? Meantime, team number 2 will come and sit in the front row here. Team 2, please come here. You have 1 minute to start.
Second team
Excuse me, for other teams, when 10 minutes are up, this will be shown. That means 5 minutes more. This means 2 minutes more. And this means it's time up.
Lithosphere process in the origin rocks. To investigate and interpret the rocks of the BW area, we have determined the process in the lithosphere. Observe the different rocks of the area, record physical features of the rock, and identify the present mineral. Produce a geological map of the area. Take and interpret measurements, runs of the geosphere, hydrosphere, and atmosphere in the formation. Determine the overall operational process in the lithosphere.
And we were at Beta Dudley and it is 15 kilometers southwest of Mysore, 12 degrees, 11.9 degrees north, and 76 degrees, 42.15 degrees. We were studying peninsular genus rocks and Sagar group, and the depth of the crust there was 30 to 35 kilometers.
From the collected data, we made a geological map to show the physical characteristics like folding, lunging, and direction of the rocks we studied.
So we took information from 3 different sites. So we were studying metamorphic schist rock, and in this rock we were studying 2 different types. There was carbonate and silicate. And in this type of rock that we were looking at, there was more carbonate than silicate. So it had more of a blackish color. It was darker. So in these minerals, there was mostly calcite, dioxide, dolomite, and tremolite. Just the major ones. And this one had bands of the calcium and silicate-rich rocks, and it was folded, and you can see how the compression folded it and uplifted it. So they were highly deformed with numerous fractures and holes. And in one of the rocks that we observed, there was a vein of calcite that had so the calcite vein, this is a picture, as you can see, straight through it there was a strip of the calcite. So our analysis about the rock, a shallow sea environment, but was then pressure from subduction was created into a metamorphic rock, and the continuous compression then created folds and uplifted rock to create the folds that you can see, it. And then more pressure created more fractures in the rock, which could have created something like the calcite vein that you can see. So if you can see, there are little ridges that are the folds from the compression. And there's more of it.
We were studying the same type of rocks, but these rocks had a higher grade of silicate and a lower grade of carbonate. This caused rows of broken silicate to form compression, and for the surface to become rough and fractured. We found out that this rock also has the presence of the fungus lightning. Here you can see a picture. And now our interpretation. This rock was originally a sedimentary rock formed in the shallow sea environment. It then underwent subduction to create the metamorphic rock with a high grade of silicate, which formed groupings of silicate. And the increasing pressure created fractures in the rock, giving it its structure and texture. And the lighting tells us that there's the presence of silicate in the rock. And there you can see a picture of the lighting.
A quarry, it used to be an old mine. It's north of Site 1 and Site 2. At that quarry, we discovered a lot of silicate and carbonate minerals. The silicate such as mica in form of magnetite, garnet, amphibole, tremolite, plagioclase, and olivine. And the carbonate mineral was calcite, calcium carbonate, and dolomite. Aside from that, we found iron oxide too. And we observed physical features there. All of the minerals were formed in small grainy crystalline, and there were some bands or groupings in the rock structures, such as in the marble there were dark and bright layer, and the dark layer we observed it as dolomite, and the bright layer we observed it as a calcite. So the analysis from the radiometric dating from the iron oxide, the rocks were aged 2 billion years ago, and that means aside from we know that the old was 2 billion years ago, we know that it's the business of life. Why? Because the forming of the iron oxide needs oxygen, and then it means there was oxygen at the present at that time, and so the photosynthesis will already exist. And we found some garnet too, and that means the rocks have undergone metamorphosis.
Sri Lanka, and I'll be speaking firstly about the formation process in the lithosphere. First thing is the sedimentation of calcite in the shallow sea. So we drew deductions from the principle of superposition. That is, we believe that calcite was precipitated due to various reasons, and mainly due to the decomposition of organic life forms such as maybe animals and plants. And second, the sedimentation, that is the formation of iron oxides in this shallow sea environment. We deduce that in this period, according to radiometric dating, as our teammate mentioned, that oxygen first appeared and came into existence. And due to the presence of oxygen at that time, iron was oxidized, thus providing the opportunity for chemoautotropic bacteria to flourish. And subduction forms metamorphism of one plate underneath another into the lithosphere. This is the primary cause of metamorphism. And the combination of both silicates and carbonates in the rock, due to the pressure exerted by the metamorphosis, and also because conditions for the formation of silicate minerals such as quartz are more suitable and are more favorable closer to the top of the Earth's surface. So we believe that this led to the combination of, that is, the formation of silicate and carbonate bands in rocks. And pressure that is within the mantle, that is within the lithosphere and underneath the crust, causes folding and uplifting. And here in this slide you can see the process of subduction in which one plate is pushed underneath another. And in this slide you can see the pressure exerted from both sides. And next, the weathering of the rock surface, that is due to the role of the atmosphere and rain that are directly related to the atmosphere. And next, the pressure and temperature change caused the silicate minerals to break, that is in situ, and these are called Boudinot structures. And the geosphere is related to this, and also due to pressure, this caused fractures. And next, consequently, veins of calcite were formed due to the dissolution of carbonate rocks because of external water, and carbonic acid was formed, and eventually calcite was precipitated. And weathering, again, from differential weathering, that is, after the rock was exposed to the surface, again, the wind and the rain caused this type of weathering. The lattice of the continental crust is older than the lattice of the ocean crust. We drew this deduction from, that is, we thought that is because oceanic crust is always being subducted because it is heavier than continental crust, and the continental crust will continue to thrive, but the oceanic crust will be destroyed. Therefore, in our observation area, the continental crust was older than the oceanic crust. And the fast depletion of the Indian crust due to the placement of its tectonic plates. That is, we all know that the Himalayas were formed by the collision of the Indian plate and the Eurasian plate. So, due to this collision, lots of crustal material is being destroyed, even every second. And that rate is faster than the formation of new crust. Therefore, we believe that the depletion of the Indian crust is due to the placement and movement of its tectonic plates.
Last 2 minutes.
To the exposed rock on the surface. And finally, we believe that long-term investigations of the area should be done to determine any changes that occur due to the movement of tectonic plates and other geosphere processes. So thank you all for listening. Thank you.
The subduction you propose for the formation of these rock. Iron oxide, which age of the rock forming is 2 billion years ago, and then the rock has to subduction. So the age of subduction is less than 2 billion years ago.
Oh, I have a very simple question. You found limestone and dolomite, right? How do you identify differentiation between, those two rocks? Is that, or how could you identify it?
Between it will react faster on calcite, but less on dolomite.
How did you see any fossils?
In the earth process, rock has formed in sedimentary rocks, and then there are subduction. So they were under the pressure, so we have destroyed it. Okay. So
The last 10 seconds to complete the answer.
okay, well, the fossil under the high temperature or high pressure, they cannot be exist in the rock. They have been destroyed for the rocks into the yes.
Thank you.
Hello. Để tôi tạm đây tôi đây không làm được.
On campus. So this is site team number 2, and this is prepared by Kirsten from Austria, Laxmi from Cambodia, Marie from France, Till from Germany, Rohit from India, Enrico from Italy, Kutaro from Japan, George from Nigeria, Maria from Russia, Mingo from South Korea, Chen from Taiwan, Tirajit from Thailand, Anastasia from Ukraine, Rachel from USA, Laya from Spain, Amrita from India, and Aisha from India. So our topic was about the hydrosphere empowering homes. So we went to this little town near Mysore, and it is called the Shivana Samudra. And we went to 2 falls, one of them called the Barachuki Falls, the other one called the Gaganachuki Falls, a hydroelectric power plant, and a solar plant. And we would like to thank our team leader, Dr. C. Nagaraju, and our volunteers, Mani, Mary, and Shreyas, for helping us throughout this wonderful project. And we hope you enjoy our presentation.
The hydrosphere, in the area we went, the climate is always like salubrious, and there are 4 main seasons. One of them is chill, one of them is rainy, and there's a kind of summer and the winter season. So the main amount of water is coming in April to November, and they have both monsoon seasons. So the one from southwest and the one from northeast. And the average amount of water is about 691.2 millimeters.
So before we went to those 2 falls, we went there at this position where the river Kaveri splits. It splits into 2 parts due to presence of very hard rocks. Their hard rocks are of granite. This you can see that this river Kaveri got 2 branches because there is a small fragment of granite present between them, because of which the river divides into 2 parts, one going towards right and one going towards left. They do both of them and into different falls. The reason for this was, as I told you, hard rocks of granite. And this river flowed in a cup-shaped valley between 2 hills like this. They were like this, one here and one here, and this was a gorge of a cup-shaped valley. So this river flowed in there. This complete lithology from that hilltop to the bottom of the river was completely made of granite, which was a major kind of intrusions into the regional rocks of metamorphic, which we call them Harvard-Titan metamorphic gneisses. You can see them, these lineaments, these ones. These are all granitic intrusions into the base rocks of these metamorphic rocks of gneisses. So you can differentiate between them by looking at their color. Granite appears to be very dark and heavy. Otherwise, if you look at gneisses, although having similar composition as granite, but they appear lighter due to heavy metamorphism because of high pressure and temperature under them. So you can consider that you can differentiate between those 2 rocks just by looking at them, but have to confirm by chemical test or other methods.
So what you can see here, the river is divided in two branches. One is this one you can see here. It's the one flowing in the north direction. This is the second branch. It's flowing in northwest direction. So the other one is like here. And this is the main branch. So before it's divided, it comes from here, and then it's divided at about this point. So there's one, and another one is here. The second point we went to is where you see the red star. It's called Barachuki Falls. This is, here you can see the GPS reading. The river falls down the cliff, as you can see with this picture. The cliffs were made out of gneiss in the east and granite in the west. There is a lot of sedimentation on the base of this fall. So you can see here's a lot of sedimentation where we found metamorphic and igneous rocks and also sedimentary rocks.
Yeah, our friend there, this picture is a granite. It's a plutonic igneous because, yes, it's a really heavy and hard rock. There's another one. And there we have partially metamorphosed samples of granite. Yes, they are partially metamorphosed. And now we have a few samples to show. One is a quartz, the other one is a granite, and the red one is a sandstone.
Station was a hydroelectric power station was built near the Gaganachuki Falls, and this is the first power station of this type in all Asia. And the gold mine of Kolar gold fields received its first energy. At the beginning, the central produced about 5.6 megawatts, and now it can produce about 40 megawatts of energy. There is a water reserve tank that contains the water of the river, and the water goes in 10 canals, one for each pipe, and then after that there is some controllers that can regulate the pressure of the water. The water it's the runner that is a part of the turbine, and so the runner begins to rotate. And also the couple that is the part of the central that connect the turbine with the generator. And this is a picture of a generator. This is the rotor, that part, the electromagnetical part that rotates inside a stator. Around the stator there is a wire where the AC electricity is inducted.
And it works as an anode, and one is in aluminium and it works as a cathode. And then just after we went to our fifth spot, which is the Gaganachuki Falls. Its height is about 98 meters, and the maximum record flow is 19,000 cubic meters per second. The rocks that you can see are basically granite and gneiss, which means their minerals are quartz, mica, and feldspar, but unfortunately we couldn't take samples, so we can't show any pictures of the samples and the minerals.
two table measures for optimal or better use of the resources, including electricity.
Last 5 minutes.
Okay. Ecology influences the water flow, as we could observe. The hydrosphere provides water, causing the plants remain evergreen. Due to various lithology, different kinds of soils are formed, allowing various species of plants to grow. And so our energy advice is, due to the presence of hard rocks in India, narrow valleys are formed. So that means high kinetic energy and, of course, great potential for hydraulic energy. So we actually think that more hydroelectric power stations should be built near the waterfalls.
Great thanks to Dr. C. Nagaraju, Mary Shez, and we also want to thank Tirajal for making this wonderful presentation.
Mystery of the older gneiss compared to those of granite.
Sir, it is produced in a plutonic environment with high temperature, so slow cooling of minerals, so producing bigger range of crystals like quartz and feldspar. But in gneisses, when the same granitic rocks underwent metamorphism and due to pressure and temperature, due to subduction or any other process which causes them to press, they first lose their characteristics, and finally, due to increasing pressure and temperature, they again form crystals, but they form them in constricted places. So they don't have, even in gneisses, they have to be constructed in some regions only. Some like when we got quartz, then quartz is constructed in one region, followed by other minerals in other regions. Contain silica content, because like in organ gneiss, you can see the eyes of quartz and feldspathic, but the surrounding regions will be of micas. Micas will form a linear arrangement because of high pressure and high pressure. They form linear arrangement in the rocks.
Change or the mineral composition of the rock?
Well, mineral composition remains the same, almost the same, because due to metamorphism that color changes.
No, if the mafic component is more, color changes. It's not due to metamorphic processes.
I'm sorry, but I can't understand. I can't tell the exact answer because it's not possible for me to tell what will be done there. So I'm sorry, but
minerals like biotite and harmlite. If the mafic mineral component increases, then automatically the color also changes.
But we don't know the exact process of how well the composition will change. We don't know how the more quartz and feldspar come. I would have liked to do that.
My question: 1 million years from now, or 2 million years from now, what will this waterfall system look like?
1 to 2 million years from now, what will this waterfall system look like?
Sir, due to
consult with your group, please.
Due to I think due to the continued erosion by water, even the rocks like granite will erode, so the height of cliff will get reduced. So waterfall height will get reduced because at 2 million years is much larger time. So some erosion will be there, so height of cliff will reduce.
The water body after the dam.
So can you repeat the question?
What about the velocity of sediments inside the water body after the dam?
yourself with your team. In these falls, the region is like this. The water is not flowing for all year because the river, water is flowing for all year but not with great velocities, because during rainy seasons only the water amount increases, because this is not supplied with glacial water. This water from Kaveri river is supplied by groundwater only. So during normal time of the year, the sediments will remain there only because of low water velocities. But when the rainy seasons come and lots of amounts of water is poured in, those sediments will travel, and so they will not having much velocities and will not travel large distances, because water flow is dependent upon time and upon the flow of velocity of water flowing.
Okay, thank you.
We are group 3 and our topic was geosphere and building homes. So these are the list of our team members. And then our team leaders were Professor Valenzo and Mr. Kumar. And the mentor that came with us was Xavier Juan. So we first set goals before we went. So the 4 goals we set were to 1, learn about the geological features of the area, 2, learn about the processes and technologies used in mining, 3, learn about the uses of the rock, and 4, learn about the environmental impact of mining. So we were first taken to Anaganchi village, which was 12 degrees and 5 minutes 30 seconds north, and 76 degrees 45 minutes and 17 seconds east. And where we were, the altitude was approximately 699 MSL. So this is just a map of where we were, and we were right there in that region. So we were taken to a dolerite quarry, and where we were, the total dike was about 20 kilometers long and 50 meters wide. And so the company that gave us the tour was the Jubilee Granite India Private Limited Company, and they were only allowed to extract about 1 kilometer. And so they have currently been extracting for 3 years now. So this is just a picture of where we were. So the dolerite quarry where we were was a Class B mine, which just means that it was semi-mechanized, so it was half operated and half machine operated. So these are just pictures. So currently they have dug about 30 meters deep, and they have a projected target of about 100 meters. And every year they extract approximately 10,800 meters squared.
Contact and regional metamorphic rocks with igneous bodies as intrusions. And the quarry was in the quarry proximity. The major rock type was the granitic gneiss, which is light colored on the top, and the lower one is a dike intrusion of dolerite. The granitic gneiss, as I said before, is a major rock type in the area. It started as a granite which stopped flooding like 3.5 billion years ago. And at some point, under conditions of high pressure and temperature, the minerals in the granite, the quartz, the feldspars, and the micas,
stretched, and so the granite became polygnized by regional metamorphism. The normal color of the gneiss is gray to grayish white in fresh cut, but as time goes by, weathering and erosional agents on the hydrosphere and atmosphere have weathered the gneiss, whose minerals, the feldspars, turn into clay minerals like kaolinite, and so the brown color that you can see, especially on the top part. With the help of a clinometer, we measured in the quarry the strike of the gneiss was north 70 degrees west, and the dip was 10 degrees. Now let's move on to the economically valuable rock, the dolerite. You have a sample provided there. It is transformed as an intrusion in the gneiss body approximately 600 million years ago, which is much younger than the gneiss body. It is dark colored. It is holocrystalline, which means it has the whole mass is crystallized, and the strike is north 70 degrees west, and the dip is 80 degrees. Dolerite is commercially known as black granite due to the dark color, but it is actually not a granite. It has a mafic composition. It's equivalent to the gabbro or basalt. It has plagioclase feldspar, pyroxene, olivine, and trace minerals magnetite and ilmenite. And an interesting feature are the joints in this rock. They are fractures which occur without lateral movement. You can see them there. As I said before, the dolerite is the only economically valuable rock. The granitic gneiss is not extracted due to its high degree of weathering, and also the dolerite containing joint is not extracted. Now let's move on to how mining goes.
Moving on to the actual bit of mining, the first thing they do before they mine for rocks is that they use a diamond-coated drill to test the prospect of the potential of the rock. This is a vital part because without drilling, you can't make a solid decision about the condition of the rock underneath. Now, diamond is one of the hardest substances known to man. Of course, the diamond used here is not the natural diamond you find in expensive jewelry. It's just cheap industrial diamond, which is almost same in hardness. And moving on to when they have found a suitable supply of dolerite, they use tungsten carbide drill bit, tungsten carbide, which is also one of the hardest substances known to man, to drill the rocks in 3 dimensions. And after they have drilled the rock in 3 dimensions, they use a diamond rope saw to extract large blocks from the parent rock. You can see the steel rope there. It is coated with small particles of industrial diamond. And on the right side, you can see the very powerful DC motor used to drive the saw rope. And even though diamond is very hard, and the DC motor used there is very powerful, it might take about 2 days to get some gigantic pieces of dolerite out. Now, the giant pieces of dolerite, the blocks, they are too large to be transferred from one place to another. So these large pieces, called parent rocks, parent stones, they have to be cut into smaller size blocks, and they use a pneumatic hammer drill to bore holes in it, and drilling bore holes in the parent rock, they they to drill holes in the parent rock, they use a pneumatic drill, and to reduce the amount of dust forming, they spray water on the drill bit every time, so you can see the air compressor, the workers using the pneumatic drills, and the water reservoir they collect water from. And moving on to the next slide, they pour in a chemical called expansion mortar, which is imported from China, and they mix it with water in a ratio of 1:5. When they pour the expansion mortar into the holes drilled 9 inches apart from one another, it expands and splits the rock into sizable blocks of 3 meters in length, 2 meters wide, and 2 meters high. And then they are transported to the processing plants, the details of which will be explained by my teammate. Thank you.
So the machines in the factory are using cutting the rock to smaller pieces by using blade of lead and water. This is really a good connection between the earth systems. The water are the hydrosphere, and they used to lubricate the surface of the rock. The rock is the geosphere that it was mined in the quarry, and biosphere is the man that will use in the rock in the continuous for his own needs.
5 minutes more.
So, and biosphere is the man that will use in the rock in the continuous for his own needs.
5 minutes more.
So, after the process, they will get their final shape. The ceramic method I used to polish the blocks, and by using this, they polish the blocks with water, and this machine that the man is working with this.
Noise pollution created by the factory. That's the reason why the factory is settled in non-residential areas. Furthermore, the open pit mining wipes out the environment above it. They can fill the hole and plant new vegetation after the extraction is completed, or the environment takes a long time to recover naturally. Another important part are the safety concerns. Safety measures taken as a precaution include gloves, helmets, and boots which protect from falling debris. Masons have to wear goggles, masks, and earplugs.
For last, I'll tell you about uses of dolerites. We use dolerites in many parts, in many ways in our lives, like this, and we can see it in our lives, like in exterior of buildings or monuments, stairs, and place for gentlemen, and concrete arrogance, arrogance. So this is our presentation, and thank you for your attention.
Makes it very strong, and because of its beauty, it is used as exterior cladding in many places, as you have seen on the staircase and in the bathroom and places like that. And these are the main properties which govern the use of stone in building: its beauty and its durability.
The dolerite is dark because of its mafic composition, its basic composition, because of the pyroxene, the amphiboles, and the olefin. They are dark minerals.
Do you consider the dolerite a Precambrian rocks or lower Paleozoic rock?
Sorry, can you repeat the question, please?
Do you consider your dolerite a Precambrian rock or lower Paleozoic rock?
Precambrian or lower and
This is, do you consider the dolerite as Precambrian or lower Paleozoic?
Yes, I think it is lower Paleozoic. It's somewhere between 500 million and 600 million from what we researched. So I think it's lower Paleozoic.
Say it again, please. You think it's lower Paleozoic?
Yes.
So the borderline between the Precambrian and Cambrian?
Yes.
What is it? The boundary. You ask your friend.
It is 570, so yeah, probably lower Paleozoic. The age of
your age is 600 million years, isn't it?
It is 600. No, actually it is between 500 and 600, but most sources said 600. So
it's settled between the.
It is somewhere the borderline between them, but we can't know. We don't know for sure from our research.
The last question.
Is the dolerite younger than the rock it has intruded into?
Of course, it is younger than the rock it intruded into, because it is supported by the law of intrusion, a vital part of basic geology.
Okay, thank you, team number 3. I request team number 4 to begin with their presentation. But before that, a photo session. And team number 5, take to assemble in the front 2 rows.
is our presentation.
And this are our goals. Firstly, study of corrugator surface belt. Second, GPS positioning. Third, study of rock history, structure, texture, and analysis. And fourth, role of geosphere, hydrosphere, and atmosphere in rock formation.
Activities carried out, location spot, we show the strike and dip of the rocks, maps the geological present, investigated the structure, texture and mineral, formation of the rock, grade of metamorphosation, chronological ordering.
Okay, here we have a map of the region we visited. We visited stations 1, 2, 3, 4, and 5. Wherever we could see foliations, we have also marked the strike and dip directions.
The graph over spots we visited according to height. Okay, the first rock we saw was called Fuchsia Quartzite. It looks a lot like this. Okay, we fly at this location, and the strike and dip is at. Okay, the rock had many identifying features. It had a very granular texture and a crystalline texture. It was also composed of muscovite, schistite, and quartz. It was converted from when it was first formed, it was a sandstone, but then as it was buried and it became metamorphosized into the rock shown. And then this is the quartz vein that was running through one of the rocks we saw. And then this is an example of one of the rocks. It was formed about 3 billion years ago, and in an ocean basin where it was made into sandstone and then later formed into the rock.
Okay, this is the spot 2 with the second rock. It's called current bedded quartzite. And this rock, we can observe the cross bedding and the horizontal bedding. Everywhere we go, we measured the latitude, longitude, and the elevation. And we also measured the strike, dip direction, and the dip angle of the rock. Alright, this rock it has a cross-bedding texture, and we can also observe that there's crystalline texture in it. So we conclude that the main mineral in this rock is from quartz. The total weight of this rock is sandstone, and it underwent metamorphism, and we can see crystalline texture. Although it underwent metamorphism, but we can still see the cross bedding and the horizontal bedding is well preserved, and its original metamorphism. In my hand here is a 3 billion year old rock sample that I collected that day, and it was once an ocean basin. So when sandstone is deposited into the ocean basin, and it's subducted, and it underwent a metamorphism. And even though it underwent metamorphism, that you can still see the horizontal bedding here, and it's still well preserved here.